All right, welcome back to the online causal inference seminar. Today we're very excited to have a fantastic speaker and discussant. We have Zijian Guo from Rutgers University, who will talk about multi-source learning with minimax optimization from adversarial robustness to causal invariance. And after that, we'll have a discussion by Kaizheng Wang from Columbia University. We also today have two collaborators of Zijian in Q&A, so feel free to ask any question in Q&A, and the collaborators are happy to help you out. Yes, without further ado, thank you all for coming, and Zijian, please take us away.
Okay. So this is the full screen right now.
Now it is. Yes.
It's the full screen and it's moving.
Yes.
Okay, great. Yeah. So thank you all for coming, and thank Dominic for inviting me, and also all the organizers for inviting me and introducing this talk. So it's really my honor, like, to present some of my recent work in the online causal inference seminar. So I'm going to talk a few works, but I put them in like host in the same under the same theme, and then discuss the connection between the distribution robust and the causal inference or causal invariance learning. Okay. So the problem I will present is from the multi-source learning. So that means the data from different institutions or from different sources. For example, here we got data from 4 different sources, and then we try to leverage the information from across all of the 4 different sources, and then transfer the shared information to a target institution. So that's the main goal of this multi-source learning. And for the particular data type, so we are thinking like this. We got this as an example here. We got 3 different institutes, and then these institutes can be hospitals. For example, like for the like 3 different hospitals, and for each hospital, we can have observation of the covariates and also observation for the outcome across different hospitals. And our goal is actually try to build an accurate prediction model or generalizable prediction model for target hospital. And for target hospital, maybe it's a newly established hospital, so we do not have as much information. So as an example here, we may just have some covariate observation, but no outcome observations. So this is an unsupervised setting for the target hospital, or we may have like a covariate observation, also a little bit outcome observation. So in practice, typically for this new hospital, it's hard to get a lot of like outcome annotation, because it requires like some specialists to review the patient and then label the outcome. Okay, so this is a basic setup, and also this multi-source learning is not just for like hospitals or like it can actually be applied for a lot of scenarios. For example, if the data are collected from different time, different locations, and also from different like people doing the environment, so that's actually the multiple batch data. And in this case, we also have the issue, and also the data may come from like a different ancestry. Okay, so the main goal of this multi-source learning is we try to think about the data. They may have this distribution shift, and we allow there exists a distribution shift, but we try to learn that's information that can be shared across different distribution, and then transfer the information to a target domain. So in the whole talk, I will try to advocate this minimax framework. So not the minimax optimality, but it's a minimax optimization. So basically, I'm going to give more details later, but here just a brief overview. So we try to look at this data from X and Y from a target distribution, from a possible target distribution, and then I evaluate the risk, and then I do a maximum of this risk. So that's the worst case risk, and then I do a minimization of this prediction model F. So in this way, we can define this prediction model F star, and then we can study like the property of this F star. I see a question from the chat. Oh, okay, thank you. So we'll talk about 3 problems. The first one we'll start with is the distribution robust problem, and then we'll move on to the transfer learning, and then we'll come back to this the inverse learning problem. And as the cartoon illustrates here, so the main difference is this uncertainty class C is different, and just by like choosing this uncertainty class C in a very careful way, we can actually achieve these 3 tasks under the same framework. Okay, so let me start with the first part, the distribution robust machine learning, And this part also will introduce the main idea for this distribution robust optimization. So let me review the data. For the data we are thinking about, for each source data, we got both X and Y observation. And then for the source data, we assume this PLX is the covariant distribution for the L source data, and PLY Max is the conditional outcome distribution for the L source data. And this is just notation. And for target, we got the covariant observation X here, and we do not have outcome observation Y here. And we use the QX to denote the covariant distribution, and QY Max to denote this conditional outcome distribution for the target domain. Okay, so this is a particular setting we're going to look at for in the following few slides. And then this setting actually has a name in this machine learning regime. It's called unsupervised domain adaptation, because in the target domain it's unsupervised, and we try to do domain adaptation. So that's why it's called unsupervised domain adaptation. Okay. So for this case, how can we define this distribution robust model? So the first thing we try to introduce is uncertainty class. So across the source and target, so we allow that the covariant distribution can be different, and also we allow that the conditional outcome distribution can be different. So we try to allow as much data heterogeneity as possible. And in this case, we actually we realize that it's impossible for us to identify this conditional outcome distribution. And the only thing that we can do is we try to find a class and such that it contains this uncertainty, this future true target population, but we never know where it is because we don't really have outcome observations on the target domain. Okay, so we actually define this uncertainty class in this form. So the QX is identifiable because we have covariant observation from the target domain. But the outcome distribution is not really identifiable. But what we do is we just imagine it come out of a mixture of this source conditional mean distribution. So that defines this class of distributions. And then if the true conditional outcome distribution is really a mixture of the source conditional distribution, then actually this uncertainty class will contain this true target distribution. So after we define the uncertainty class, we can think about, let's say this T is anything from this uncertainty class, from this one of the future target population. And then with this T, we can define the performance of a prediction model F. So we can think about F is any non-parametric predictor, such as realized by random forest or realized by neural network. And then for such a prediction model, we can do an evaluation, like how much what's this prediction error, and we compare it with this null estimator. We use a 0 to predict y. Okay, and then we can define the reward function. And this reward function basically says that for this targeted population generated from distribution T, so how good is the performance of the F? And we hope that this reward to be as large as possible. That means a lot of the information from the Y can actually be explained by this F. Okay, so remember that we really don't know what's the future target, and we only have a class of populations that may contain the future target. So what we can do is a very intuitive way. We're just looking at the worst case performance. So if for this prediction model, for any target population, we got the reward, and let's just look at the worst case reward. And that measures the performance of this prediction model and across the whole uncertainty class. And then we just try to maximize this worst case reward function. And that's what give us this definition of F star. Okay, so this is just like a poor man idea. Like if we don't know where the target, then let's just brainstorm all possible future target and then minimize or maximize the worst case performance of a prediction model. Okay, so this is a graph illustration. Let's think about a concrete example. Let's say we got two hospitals. In one hospital we got 9,000. The first hospital got 9,000 observation, and the second hospital we have 1,000 observation. So this decomposition 90% and 10%. So if we implement the empirical risk minimization, we basically try to optimize the prediction performance for such a population. But let's imagine if in the future we go to the other extreme. So the first hospital becomes the minority, it only has 10% observation, and the second hospital has 90% observation for the target. So in that case, so this will be actually our target. And then the model we trained for this source mixture may not work well for the target. Okay, so that actually explains why ERM is not in general, is not a good method when there are distribution shift. And what exactly this distribution robust optimization is doing is actually like try to exhaustive search all possible like future target population, and then looking at the worst case, and then try to do an optimization of the worst case component. Okay. So before I move on, so any questions for the definition of this group distribution robust models? Because it may be slightly new for the statistical perspective.
I think there are no questions. Yeah, thank you.
Okay.
Oh, for a question. So you allow arbitrary mixtures in Y given X? Do I understand that correctly? You don't restrict that in any way?
It's just from, it's a very good question. Just from a simplex. It's not from anyway for the moment.
Okay.
Thank you.
Thank you.
Yeah. Actually, according to Dominic's question, actually there are a lot of criticism for the group DRO and for the point that this could be too conservative. So imagine the future is just one point, but we're looking at all possible convex combinations. So even though it belongs to this one point, it's this point, but it could lose a lot of information. So to address that, we actually can incorporate a little bit of information H. So if we know like the mixture is belonging to this uncertainty class H, then actually we can define this a minimax optimization problem by incorporate this information H. So that's how we can like get more accurate, like get a smaller uncertainty class. And actually, like some cases we may have wrong prior information. And in this case, we have like a misspecified prior information, and then the prediction model will actually be not that accurate. Okay. So the first main result from this paper is how can we solve this minimax optimization problem? It actually seems very hard to me at the very beginning, and then actually we can identify a closed form solution. So a little bit more notation. So for the conditional mean distribution, we can use FL to denote the conditional mean from each source. And then we write down the same like a minimax optimization problem. And then actually after some like mathematical derivation, we actually can show that this FH star is just a convex combination of this FL. And this FL is the conditional mean model from each sources, and the gamma is the weight I'm going to explain a little bit later. Okay, so this actually provides a way that we can compute this FH star instead of solving the minimax problem. We can like estimate FL first, and then like estimate the weight, the gamma secondly, and then we can do a ensemble to estimate FH star. Okay, and how do we define this gamma star? So the gamma star is actually a solution for optimization problem. So we first need to define this matrix gamma. So it's an L by L matrix, and then it measures the similarity between FL and FK. Okay, after we got this gamma matrix, we can do this quadratic minimization, and then we use the prior information. So if we have no prior information, the H is just a simplex. But if we have some prior information, we have this expression. Okay, and the condition for this theorem is actually quite mild. First of all, like this function class, it need to be convex here, and also need to contain like all of this condition mean model, and also we need H to be convex, and then we have this result. Okay. And this is for general machine learning or for like non-parametric regression. And like I would like to mention that this idea was first established by Nikolai Mansosha and Peter Bowman in their 2015 annals paper, and later by a paper myself, like extending their results to the covariance study. Okay. And then we actually, from this observation or from this theorem, we can have a geometric interpretation of what exactly this F star. So here we got 6 different condition mean distribution, and then we have a convex combination of them, and then the F star is just the one that's closest to the origin. So that's the definition. That's an equivalent way of looking at F star. So basically, if we got the condition like heterogeneous distribution, then we can just find the one that's closest to the origin, and that's the another way of interpreting this this distribution robust optimization like solution F star. And if we got some prior information H, then actually we can incorporate that. Instead of looking at the whole convex combination, we can look at the convex combination belonging to H, and that's the projection FH star. Okay. And after this, we can actually think about how do we estimate it in a data-dependent way. And very intuitively, we can estimate everything just by machine learning, say by a neural network, and then we can plug in to estimate the gamma, and then we can ensemble this F hat L, and then to have this FH tilde. So that's a very intuitive way of how do we estimate FH. But actually here, I would like to like mention a point, like how we can apply the useful statistical idea to even improve some machine learning prediction model. So let's say this plugin estimator, we just do error decomposition, and then you just copy the definitions, and there is a main term for this error decomposition. It's this first order term. So it measures the difference between f hat L and FL, and then multiply by f hat K. And this is just the first order term. And actually for this term, even though like asymptotically it will still go to 0 if f hat L is a consistent estimator of FL, but actually in finite sample, we can improve it. And the way to improve it is also simple. So this FL is what we don't know, but what we really have is we may have a consistent estimator or unbiased estimator of FL. Let's say if the xi and yi, they are following this distribution, then actually the yi is like automatically an unbiased estimator of this FL. And we can simply replace this FL by the yi, and then we use this way to estimate the weight, to estimate this bias. Okay. And also in practice, we may not have data sample from this, but we can actually do some density ratio weighting to get a good estimator. Okay. So if you're familiar with like double robustness or double machine learning, so this is actually the idea we borrow from that literature, and then to improve the estimation of this weight matrix gamma. And actually, I'm omitting a lot of details, but the final takeaway for this proposal is when we do aggregation, we actually can do a more accurate aggregation. Instead of using the plugin estimator, we can do a bias correction by borrowing the idea of from the double machine learning or double robustness literature. We can get a more accurate estimator here, and then we can get a more accurate estimator of gamma hat, and then we do the example. Okay, so in the paper we at least here we show that in terms of rate of convergence we have improvement after doing the bias correction, and also like in terms of finite sample performance we have a better performance after bias correction. But for the sake of time, let me just postpone like that to the if you're interested, you can read a bit of the paper. Okay. So we have talked about the distributional robust learning, and then we're looking at this uncertainty class as this simplex or slightly less than the simplex is this the H. But actually, we can do better by generalize this idea to the transfer learning setting. And what's the transfer learning setting? For the transfer learning setting, actually, we not only have the source information, we also have the target, for the target data, we also have some outcome observations. Okay, and that's an illustration of the data. So for the previous setting, we only have the source outcome, but now actually for the target data, we also have some outcome observation for the target. So that's the main difference from the previous setting. Now we have more information from the target domain. And also this is similar notation as before, but just to simplify the discussion, we only focus on the linear model. And we use the beta L to denote the condition mean model from each sources. And then for the beta 0 is the condition mean from the target. And our goal is to recover the beta 0. Okay, so the goal has shifted because in the previous setting, there's no way we can identify beta 0. But in the current regime, we do have some outcome observation. So this gives us the hope. Okay. So now let's think about how can we generalize this distribution robust idea. And the most important thing in the distribution robust idea is this uncertainty class. And how can we generalize that from this like unsupervised domain adaptation setting to the transfer learning setting? And the first thing we do is we actually enlarge the uncertainty class. So we include this source mixture, also include a target here. So it's a mixture of the source and target. Okay. So the advantage of this is this must contains the target population because we can set the Q0 equal to 1 and everything else to 0. So that will contain the true target population, Q, Y, given X. But the bad thing is it makes the uncertainty class even larger. And the second step, so here is actually the most important takeaway of this work. So we actually can use this information from the target domain to filter out the arbitrary source mixture and all the target mixture. Okay, so if we look at this mixture of source and target, any source and target mixture Ty given X, we can actually evaluate this prediction model and evaluate on the observed target domain with the target outcome observations. And then if this risk is kind of like not so much worse than the benchmark risk, the benchmark risk is we just use the true conditional mean outcome model and then use this one to denote this the noise level or the benchmark like risk level. And if this mixture of source or the target is not performing much worse than the right-hand side, then we'll keep this source mixing or this mixture of source and target. Otherwise, we'll just throw away because it will be discarded from this uncertainty class. Okay, So that's kind of the main idea, like how do we use this target data to filter out like arbitrary mixture, but only retain a small set of mixture that performs well on the target domain. And here, tau is a training parameter. So we typically choose it as 1 or NQ, but you have other ways to choose it. And also this tau actually reflects like this user's belief about what kind of tolerance we would like to have, like how much worse we can this mixture source may perform, like compared to just using a target only estimator. Okay, so that's the key part for this building the uncertainty class. And the takeaway is we just build the uncertainty class such that the mixture source and target, it performs reasonably well on the target, and that's the only part of uncertainty class we'll keep. Okay. And build on that, we can actually generalize the definition of this distributional robust model. So we can define the loss function or the reward function like this. So instead of compare to this zero estimator, we'll compare to any initial estimator. And we can also put this initial estimator as a zero estimator. Okay, so we can compare, like you can use this one as a reward, and then when we're looking at this uncertainty class, we're actually looking at a bigger uncertainty class. Sorry, a smaller uncertainty class. We put it as a C tau. C tau is defined here. So it's only uncertainty class, only possible target population or mixture source and target, such that it performs well on the target domain. Okay, so that's the definition of the Garter estimator, and it actually extends the idea from like a distributional robust learning to the transfer learning. Okay, so maybe I should pause here a little bit to see is there any questions? Are there any questions?
Thanks. There are no questions in Q&A right now, so yeah, please feel encouraged to pose questions there. Yeah, one quick question that I had. So you mostly use quadratic loss here. So how much of a chance do you think we have to generalize that to any type of loss function, or let's say a specific loss function like logistic regression?
Yeah, we actually we are working on that direction, like how to. It's a good point. So it's definitely generalizable. But as you may know, like the generalized that the cost is we do not have the closed form solution. Yeah. So that's the cost, but it's generalizable with a non-trivial effort, I would say.
Thank you.
Thank you. So as Dominic pointed out, like if we use the least square loss, so the main advantage is actually we have this kind of closed form expression. So it's a weighted average of the beta L, beta 0 and the beta L, and then we can have a weighted average. We can compute the weight in this form, and then that's the identification for the Garter estimator. And then the gamma star is actually computed with a similar format as before. So it's this quadratic minimization, and then we're only looking at this like S tau belonging to this uncertainty class. So that's one, make sure that the mixture source and target performs well on the target domain. Okay. So I'm now going to present the full procedure here. You can take a look at the paper for the full procedure, but I would like to highlight the main idea for the construction and what's the benefit of using this Garter estimator. So let's think about the setting. We got a lot of source data, and for the source data, we can run this lasso estimator, and we show that if you assume the true condition mean model, then we can show that the lasso estimator has this rate of convergence. Okay, so just remember this NL can be huge. So that's actually and the setting we are looking at. And for target domain, we can also implement lasso, but because of small sample size, we only have this rate of convergence. The NQ is much smaller, and then we can just do the plugin estimator as mentioned as hinted by the previous slide. So we got all of the beta hat 0 and beta hat L, and then we compute the weight, and then we do aggregation. We got this Garter estimator. Okay. So the rate of the Garter estimator can actually be established like this. So this is a very nice result established by the moderator Xin. So she is able to show that for the Garter estimator, it converges to beta 0 at this rate. So on the right-hand side, let's look at the minimum, like term by term. So the first term is k log 0 log p or NQ. So this is something very familiar. So it means that I just use the target only estimator. Okay? So that's corresponding to a scenario if the mixture source is different from target. So then there's like little hope we can do anything to borrow the information from the source. So what we can do is we just use the target only. And the right-hand side is actually corresponding to another more favorable scenario. So let's say the mixture source is close to a target. So in this case, the alpha is close to 0 or exactly equal to 0. So that's plotted by the right-hand side. So you can see when alpha is exactly equal to 0, then this tau, like we choose as a 1 over NQ, and then for the whole thing is a constant over NQ because L is typically small. Okay? So that's much smaller than the first term because the K0 is typically much larger. So that means if you compare the left and the right, when the alpha is close to 0, then we basically compare the first term and this term. And we also mentioned that for the source, we typically have a huge sample size. Then actually, the second term is smaller. It means that we can improve the target-only estimator. Okay, so the takeaway message are two. The first one is actually, as long as the source mixture holds, then actually we can have a much better rate of convergence than using a target-only estimator. And the second one is actually here we do not make the assumption that the source mixture or the mixture source is close to a target. Okay, so it's all data dependent. So if the data thinks they're close, then we got a better rate. If not, then we got kind of the classical rate. We just apply the lasso estimator. Okay, so we actually apply this to a scientific problem. So we try to use this to do this the HDL, the HDL is an important blood measurement associated with the cardiovascular disease. And each time when we do this physical assessment, the doctor will blood test, they will measure the HDL. And actually, it's also known that the genetic variants, they predict HDL, or the association between genetic variants and the HDL varies across different ancestries. So for people with different races, then their association is different. So the question we're asking here is, how about for the mixed racial group? So say one parent is white and the other parent is Asian. So for this small group of population, so typically we do not have that many observations, and also there are less studies carried out for this small group of populations. Okay? So what we exactly do is we apply this, we use the UK Biobank data. UK Biobank has the people labeled as white, black, Asian, and others with their sample size. And then for each of this source population, we build a prediction model for HDL. And also we build a prediction model for HDL using the target data. So that's this white and Asian, one parent is white and one parent is Asian. And then we evaluate what's the output of the GART estimator. So the first output is actually GART estimator is a weighted average. And as you can see from here, the GART estimator is doing the right thing because it's using the target estimator, and also it is using this UKB white and UKB black. Okay, so even though we don't tell the machine what exactly we'll see, but it's actually using the correct information. Okay, and also if the target is the UKB white and black, so in this case we can see that the GART estimator only use the UKB the target domain, and also the UKB white and the UKB black. Okay, so it means that at least the GART estimator is doing something sensible from intuitive point of view. And then we actually evaluate the performance on out of sample performance on a target domain. So we use the white and black as a target domain, and then there are 50 observations, and then we evaluate its MIC and compare that to the MIC of just using the target only estimator. Okay, and then we compare how much we can improve the MIC, and we see that for the GART estimator we do have improvement, improve more than 60%. And we also try other state-of-art methods like max-min and trans-lasso and trans-GLM. So I would like to report the result in a positive way, in the sense all of this multi-source learning method or transfer learning method, they do have encouraging results for these practical applications. So they all improve the target-only estimator. Okay, but some are more and some are less, but it all depends on the particular data application. Okay, and we also actually try to think about what's the difference between the GART and the trans-lasso trans-GLM. So we actually try this the trained model using the UKB white and black as a target on a different data. We try to test this generalizability. So we train the model on a data and we evaluate on a different one, and we can see that the GART estimator is a little bit favorable here, and we interpret it for the reason that we apply the distribution robust idea. Because when we do the distribution robust, we're not only just optimizing what's for the target, we're optimizing like an uncertainty class containing a target. And then from that perspective, so if the distribution, the future distribution is even slightly different from the current target, So we may have some more guarantees. Okay. So that's the main part I would like to talk about for this like a guided adversarial like robust transfer learning. So if you got like more interest about this, you can take a look at our paper here. Okay. So in the final part, I would like to come to this like connection to the causal invariance learning, and I would like to show this figure. So, but before I move on, so I would like to check again. So, is there any questions?
And no questions in Q&A right now. Thank you.
Okay, great. Then I will just move on. So, what we have discussed is we use this minimax optimization, and we can use that to handle this distributional bus optimization. We can use that to handle the transfer learning by leveraging like the target label data. But also, I would like to mention that this is something surprising to me. I just realized maybe like a year ago. Actually, we can also using this minimax optimization to do this causal invariance learning. And as you can see from this cartoon here, so from distributional bus to transfer learning, we got a smaller uncertainty class, but we can think the other way. So what if we got a larger uncertainty class? And then in this case, actually, we can do the causal invariance learning. Okay. So before I actually need a few slides. I will try to briefly review what is the causal invariance learning, and then I will come back to discuss how can we use this causal invariance. So how can we use this minimax framework to attack this causal invariance learning problem? So for the causal invariance learning, so it's also in the multi-source regime. So it assumes that for data from different sources, they share a same causal model. So all of this L sources, their true causal model for Y is the same. It's a beta star, S star, and S star is the set of the causal variable. So as the illustration here, so the causal variable is X1. So in the two environment or in the two sources, so this X1 affects Y in the same way, but Y affects X2 differently. Okay. So in this case, the S star is just equal to 1, and X1 is a causal model. And for the causal invariance learning, it assumes that the causal model is the same across different domains. But for the non-causal one, so for example, the Y1, the Y to X2, the relationship could be different or could be heterogeneous. Okay. So then how can we identify this model? We can actually identify a model B such that this prediction model, the variance of the prediction model is actually stable or shared across different domains. Okay? So that's actually the main idea for the main idea for the causal invariance learning. So we try to find a prediction model such that it has a stable performance across different domains, and hopefully we can differentiate X1, X2 by leveraging the information here, because only X1 affect Y1 in a stable, in a like invariant way, but X2 affect Y in a like not invariant way. Okay, and let's look at what's happening in the literature through this twice example. So for the twice example, same structure as before. The X1 is a true causal variable, and X2 is affected by Y. And in this case, we assume that the model for the outcome model is invariant. But we also need some heterogeneity. So for the first environment, so we intervene like this X1, the generation of X1, X2. And you can see the two hammer here, and the hammer actually means like how much intervention they have received. So if they receive a small intervention, then the hammer is smaller. And if they receive a bigger intervention, the hammer is bigger. So it means that for the second environment, so we intervene this two noise level more than the first environment. Okay. And then how can we identify like which variable or which model is invariant? So the most natural idea proposed
Zijian,
by the
sorry, you have around 10 minutes left, just to remind you.
Okay, great, thank you. So the first most natural idea is actually to enumerate all possible subsets. So if we enumerate all possible subsets here, and then we can get the best prediction model and evaluate its risk across different sources, then actually we can see whether risk depends on L or not. In this case, we can see that only when we include a true causal variable X1, so we have an invariant risk. So that's the intuitive way to identify this S and also identify the beta star. Okay, and later there's a nice extension of this exhaustive search idea to this optimization problem. So they can do a penalization here and then to achieve the similar goal. Okay, so the proposal here is actually nice, and then they propose the first method and state-of-art method to identify this I star and beta star. But the issue is it's actually either based on exhaustive search or based on this like integer programming. So it's very hard to like scale this up. So if say p equal to 20, then both methods may not implement well, okay, because they take a lot of time. And what's our proposal, as promised from beginning, is we actually can enlarge this answering class. So we include some negative weight. And then this gamma, like we can put the gamma to be very positive, and then we can get answering class like this. And then we take the maximum risk in this format. So not just inside the like simplex, but actually we can include some negative weight. And then we can do this minimization, okay? So as promised, so this is also a minimax optimization problem, but we just make the answering class larger. And the first question I try to answer here is why this will give us an invariant risk prediction model. So actually, so the first equation is so maybe you can trust me. So this is actually is equivalent form as this maximization problem. And we can actually show that the negative DRO or negative weight DRO as our proposal admits this following form. So it's a minimizing like a summation of two parts. So the first part is the maximum risk, and the second part is a risk disparity. So this term measures the difference between the maximum risk and the average risk. And then if you put the gamma, the radius of the answering class really large, the gamma equal to infinity, then we force that the second term has to be the same. So it means that we have to have a prediction model that its risk is invariant. And that's give us this constraint. And then if the risk is invariant, then the second part is dropped. Then we just minimize this shared or the invariant risk. Okay, so that connects this negative DRO and this invariant risk prediction model, and by the above observation. Okay, and I hope like this convince you that we can use this minimax problem to solve this the causal invariance learning problem. Okay, at least it provides one solution. And in the following, actually, I will try to answer two questions, but maybe at a brief level, but I hope to pass the main message. So the first question is, I have mentioned that the existing state-of-art method is either based on the exhaustive search or based on some integer programming. So it's hard to solve it very fast. But we are going to show that actually for the negative weighted DRO, we can solve it very fast, and also we have some theoretical guarantee, like it definitely converges to the global minimum. And for the second question, and label that question 1 here, we also try to answer is, in what scenario can we actually identify the true causal effect? So in the literature, there are some high-level conditions, but it's actually unclear, like how many interventions or how many environments do we need such that we can identify this like true causal invariant model. Okay, so we're going to answer both questions. So in the paper, actually, we couldn't answer both questions fully. We can only answer both questions in a very specific like regime, like it's called additive intervention, and Dominic is a leading expert on this direction. Let me briefly introduce what's the additive intervention. For the additive intervention, we assume the same causal invariant model, but also we assume that there is a generating model for XL, that's the order covariance. And then the noise is actually driving part for having this heterogeneous distribution. And then the noise is actually generated as the noise here and plus some intervention. And the intervention delta L is the intervention we can add to each environment and to generate heterogeneous distribution. And actually, that's why it's called additive intervention, because we add the intervention to the noise level, and then it generates this like additive. It generated the heterogeneous distribution. Okay, so that's actually the only intervention we focus on in the paper, and we can provide a full solution based on the previous two answers. So for the first answer, when can we do the causal discovery? So we can actually do the causal discovery if there exists a convex combination of the covariance matrix of the delta L from a collection of environment is dominating the other collection of environment, the covariance matrix from another collection of environment. In this scenario, we can actually do the causal identification. And as an illustration, so if the first environment it has a lot of intervention and the second environment does not have that many intervention, then actually this condition automatically holds. And then we can do the causal identification. And of course, we have a lot more other practical scenarios, so we can verify this. And there are two important comments. The first one is we don't need to know what's the weight. So as long as there exists such a weight, it's fine. And the second one is this one is nearly necessary and sufficient for additive intervention, because if this condition doesn't hold, it's easy, like we can construct a counterexample such that we can never identify the true causal effect beta star. Okay. So in the talk, in the paper, we actually introduced equivalent causal identification condition. So we write the matrix A omega in this form, and then we use the lambda, it's a minimum eigenvalue, so as a heterogeneity measure. So if the lambda is positive or it's a constant, it means there is a lot of heterogeneity across different environments. And in the paper, we actually have shown that if there exists a weight such that the minimum eigenvalue is positive, so it's equivalent to the previous condition, there is a collection of environments dominating the other collection of environments. So they are equivalent. And you can refer to the paper to see the exact proof. And Zhenyu built on this connection, like this is unexpected for me, and Zhenyu built on this connection of this first condition and the second condition. Okay. And here is the first main result. We can actually have shown that for this Minimax optimization problem, we can show that this negative DRO is converged to beta star at this rate. Okay, and let's look at the right-hand side. So the lambda is this heterogeneity parameter. If lambda is positive, then this rate will, then it's fine. And then the gamma is the radius of this uncertainty class. If gamma is large, and then we actually can make a right-hand side go to 0. So this shows that under this condition 2 or condition 1, this causal identification condition, the negative DRO will do the job. Okay, but actually it only answers the first question. So the negative DRO is actually can identify the beta star under condition 2 for additive intervention. But the other question we really haven't answered is we still cannot solve it. So the objective function here is non-convex because there's some weight can be negative, and this least square loss, and then it's a non-convex optimization. Okay, and to solve that, we actually need the following theorem, which is a very surprising result, proved by the collaborator Ifan. So he's actually an optimization expert. So he actually can show that under condition 2, so if this causal identification condition holds for the additive intervention, so for any prediction model B is close to beta star in this format. Okay, so if you can trust me, so everything else you can drop them because they always go to 0 if we choose like this mu, like that's a ridge penalty. If we choose that close to 0, so and the lambda is a positive constant, and n is something goes to infinity, and gamma is something goes to infinity. So they all go to 0. So the intriguing part is we establish a connection between the difference between B and beta star and this gradient. Okay, so if we can show that there is a B such that this gradient is close to 0, then we show that this B is close to beta star. Okay, so if you are familiar with convex optimization, so this is always the case. So if you find a point that's the gradient is close to 0, if like no constraint, then actually it's close to the global minimum for the convex optimization. But unfortunately, this is extremely hard for non-convex optimization. So in general, like finding this global minimum is very hard. But this theorem builds a connection that you don't really need to find the global minimum. You just find a point such that the gradient is close to 0. And that point is close to the true beta star. And that's the main takeaway of this theorem. Okay, so that means we just need to find a point like prediction model such that its gradient is close to 0. And actually for that part, it's much easier to do for non-convex optimization. So for non-convex optimization, finding the global minimum is hard. Finding a point such that its gradient close to 0, so that's much easier to do. And then people know that like we can just apply the gradient descent and then we can achieve that. Okay.
Sorry.
So this is
Zijian, sorry to interrupt you. So we're running out of time. So if you could wrap up in the next 2 or 3 minutes,
okay,
that would be great. Thank you.
Okay, that'll be great. I can wrap up. So then the take-home message is like we can just do a gradient descent, and then the gradient descent will give us something like the gradient close to 0 as the final solution. Okay, so this is the final message for this part. So we can actually show that the proposed estimator, even though it's for non-convex setting, we can show its rate of convergence. and this T is number of iterations, and it means we got a very long iteration, then we can show that our proposed negative DRO estimator will converge to the global minimum. Okay, so this some simulations, and here is a paper reference you can take a look, and I think that's all the main message already passed. So let me just do a brief summary. So we are looking at this multi-source learning, and this is a setup, and then we use this as a bigger umbrella to talk about both the distribution robust learning, transfer learning, and the causal invariance learning. And they can all be written as minimax optimization form. And I hope I have already passed the message from the left to the right. So the uncertainty class becomes smaller and smaller. So we got a more and more accurate prediction model for target. And from right to the left, we get more and more generalization guarantee, in the sense we're looking at more and more possible future target population, and then have a guarantee of the future target population. So this is the final take home. For the multi-source learning, I think it provides a lot of opportunities for statistician. It requires different tools from the previous single source learning, and also it's intriguing how do we define what is a generalizable model. There are millions of ways of defining that, and each one of them can have their own advantage and disadvantage. And also we highlight the computation-wise there is some challenge, and inference-wise it's also quite challenge. And here is a reference if you're interested in that. And finally, I would like to thank all of my collaborators, and thank Zhenyu and Xin to serve as the moderator. Yeah, thank you.
Thanks for the very nice talk, Zijian. I think in the interest of time, we should quickly move over to the discussion. Yeah. So Kaizheng, please take us away.
Sure. Let me start by sharing my screen. Okay, wonderful. First of all, I would like to congratulate Zijian and all the collaborators for this series of wonderful work. I really learned quite a lot. So I actually attended several of the talks before, so I got had the pleasure to learn the key ideas. And now for this special occasion, it's super nice to combine all the ideas in a very coherent manner to highlight the main theme. So I would like just to share a few comments from my side. So this is the key setup throughout Zijian's talk, that is the multi-source learning with minimax optimization. So we are already pretty familiar with the population risk minimization problem. So we have some supervised learning problem, and we want to optimize the population risk over function class. But due to the uncertainty and also heterogeneity across the different sources, right? So Zijian's approach, Zijian's proposal is to not just directly optimizing the loss for various reasons, but consider a set of ambiguity set, or a set of plausible distributions, and then to optimize the worst case loss across that set. So this general framework, this general umbrella, covers several key topics, and in particular, Zijian's talk covers 3 of them. In the language or the jargon I'm the most familiar with, the first one corresponds to unsupervised domain adaptation, where you get unlabeled data from the target distribution of interest, and then the labeled data from a bunch of source distributions. Okay, the second part is supervised domain adaptation, where the data from your target distribution is already labeled. Okay, so that's definitely more informative, and that's why Zijian mentioned you can use a smaller ambiguity set for the second part, because you do have more information about the model and distribution. And the third part, invariance learning for causal discovery. So this is a different setup. There's no particular distribution of interest, but you have a family of distributions, and you want to learn some commonality shared by all of them. Okay. Okay. So for the first part, we want to solve a minimization problem over a Q distribution. The key challenge lies in the distribution shift. So both in the covariate and also in the posterior or the model. The idea for this part is to conduct the minimax optimization for this particular loss, which represents the amount of explained variance. Yeah, the negative of this part is the explained variance. And so you look at the worst case over a family of plausible distributions so for those plausible ones, they should be consistent with our target in the covariate distribution. And in terms of this posterior, this can be any combination, the convex combination of those source distributions. Yeah, of course, the convex weight needs to satisfy a certain constraint. Okay, and Zijian showed a very nice result. Even though this formulation looks daunting, the final solution admits a linear form, right? It's a linear combination of a bunch of individualized individual learners, learn from the individual source data sets. And you can obtain this convex weight by solving some quadratic program. Yeah, so there's a very nice connection. There's a very nice result covering the population version, and then there's a nice estimator for the sample version. Okay, so for the second part, now supervised domain adaptation, we have more knowledge about the source because we have the target because we have labels. And then here, this part, Zijian focus on linear models. Again, minimax problem, max over ambiguity set. And the ambiguity set not only consists of those convex combinations over the posteriors, but also they need to be compatible with the existing label target data. So meaning that you're roughly speaking, the risk over this plausible distribution cannot be too worse than the risk over the target distribution, right? The tau is some tolerance level. Yeah. And again, this formulation admits a simple form of solution. You have some convex combination for a linear combination form, and you get weights from a quadratic program. Theoretically, you can prove the adaptivity to the unknown posterior drift, which is the discrepancy among those underlying models. Okay. And finally, for the last part, invariance learning via negatively weighted DRO, there's no particular distribution of interest, but you want to all of them share a common linear model with some support, and you want to identify this common structure, right? Again, the idea is minimax optimization. So there are two objectives per se. One is the maximum risk across the distributions. I denoted by big M, and also there's an average risk. I denote by little m. So you can the big M represents the maximum risk, and their difference between the big M and little m shows the risk disparity. So overall, you want to minimize the risk and also the risk disparity, and there's a weight factor, okay, to balance the two. And this problem admits a very nice reformulation and super interpretable. I'm very impressed by this result. So it does look like what we showed before. So it's a minimax formulation, minimax loss minimization problem. And the max, you're not just looking at a convex combination of individual losses, but you enlarge the set a little bit. So you can even tolerate some negative weight. Okay, so this is and once you arrive here, your toolbox, there are lots of tools for minimax optimization problem, and so for final sample version, you approximate the population loss by empirical one, add some ridge penalty also for the computation reasons, and finally you can use a gradient descent. That's a very nice first order algorithm to solve it. Yeah. So that's just a summary. And here I've got a few questions. Let me start with the third one. First of all, I think Dominic brought it up during the second part. How do we go beyond linear model? Because when we look at the maximum loss or the loss disparity, we need the loss values to be directly comparable. But for going beyond linear model, let's say for logistic models, the loss depends on the noise level, signal strength, etc. There, you cannot directly compare them and look at the max. So here's a cliche example in this invariant learning literature. Your X is the image, Y is a binary label, whether it's a cow or a camel. The set of useful feature corresponds to the shape of the animal. Whereas you have a bunch of sparse features telling you about the background color, right? Whether it's green background, that's grassland, or yellow, that's usually the sands. So that's something I would be interested in learning more about. And also, I think there's a key feature in this work is that even though in the problem formulation, it was motivated through a common support assumption on the beta, right? The common beta and of course common support. But this learning procedure actually doesn't explicitly enforce such structure. I think the very nice thing here is that without enforcing this common support assumption, the computation would definitely become easier. And also this framework has the strong potential to go beyond linear mode features, let's say nonlinear features, right? But on the other hand, would it be possible to get better error rates by explicitly promoting sparsity, right? If the sparsity in the linear model does hold, then we may get it better. Yeah, so maybe I can quickly go over some questions. Yeah, so another minor question that I noticed there's a non-parametric error term in the error bound, so I would definitely want to learn more about that. So just to, for the other parts, so parts 1 and 2, my key question actually lies in the impact of covariance shift, because I remember especially in part 2, the key focus is on the model shift, right? The error bound, the adaptivity is shown against the unknown error, the unknown discrepancy across the models. But I think it's a prevalent feature in all those motivating examples like hospitals or race mixture populations, that the covariance shift can also be severe. So do we have any characterization, and can we have an optimal quantification of this impact? Yeah, so that's all for the question and comments. Yeah, again, congratulations for the wonderful work.
Thanks for the very interesting discussion. Zijian, do you want to respond?
Yeah, for sure. Yeah, thank you so much, Kaizheng. Yeah, I cannot imagine how much effort you put into to ask so many insightful questions. So maybe I can answer some from I can do the backward, because for this one we indeed think about the covariance shift. Mm-hmm. So actually the framework is can handle covariance shift, but like for the first two works, we assume they're already covariant on the target domain. Mm-hmm. So we can actually estimate the density ratio model for the covariance shift. But I think the open question is, what if there's some non-overlapping assumption, or the density ratio model is not have some positivity assumption. So for that part, maybe we need to borrow your technique or to handling some of that thing. But we haven't thought about it. So I would say the covariance shift is partially handled in the paper, but under assumption of the positivity assumption there. Yeah. So okay. For this pure n to a quarter, so that one is actually we believe is not sharp. Yeah, but for our current implementation, or for our current algorithm, I think it's kind of sharp, because in our simulation, GenU actually do very careful simulation to verify what's the dependence on n. And actually dependence on n is n to a quarter, and which is unfortunate in our current implementation. But there are ways maybe we can improve it. For example, we do some future screening first, and then retain this I star first, and then we do a standard pullover. So I think that may resolve the problem. Yeah. So for the previous one, the beyond the linear model, for both of the two questions, I don't think we really have an answer. So for beyond the linear model, we do have answers for part 1 and 2, so they are ongoing works. But for this causal invariance learning, I think it's a much harder problem. So as discussed in the talk, so we can only solve it for the additive interventions, which is already a special setting for linear model. It is not the full linear model. Say do intervention, we don't know how to do it. So I think the linear model definitely it's a great question, but we don't know how to solve this linear model assumption. Yeah, and regarding this common support, yeah, actually, yeah, I don't have a good answer for this, but what I want to comment is so for the causal invariance learning, I think important thing is to learn the causal variable. So it naturally will come with S star. So some variables shouldn't be included, not because they are not strongly associated with outcome. It's because they are not stably associated with outcome. So they are discarded. So that's why I think they need the S star. But in our current implementation, we don't really learn the S star directly. By the way, I mean we don't do enumerate all possible subset, or we don't do this integer programming. So we kind of avoid it in our algorithm. But I think for the model assumption, we do need that. Yeah, and I also want to make a comment. So the algorithm can actually be extended, but the only way or the only regime we can establish the theoretical guarantees for this additive intervention. Yeah, that's a limitation. But the algorithm like this negative weight DRO, so we believe there may be more potential in other regimes, say in do intervention or in some hard intervention regime. Yeah, that's our current belief. Yeah, thank you so much, Kaizheng.
Yeah, thank you, Zijian.
All right, awesome. I think in the interest of time, we should quickly wrap up. So first, yeah, thank you so much, Zijian, for an interesting talk, and Kaizheng for a great discussion. Thank you all for coming. So next week, we're going to have Sam Pimentel from UC Berkeley, who will talk about design sensitivity and its implication for weighted observational studies. Yeah, thank you all for coming. I hope you have a great week, and see you next time.
Yeah, thank you. Thank you, everyone. Bye.
Bye-bye.